Excellent and ATARRI Consortium. I'm very pleased to welcome you on this session, part of ATARRI Expert Talk webinar series. ATARRI stands for Atmospheric and Solar Research and Innovation. It's a Horizon Europe twinning project founded by European Union. Its core aim is to enhance research, excellence, and innovation capacity in atmospheric science and solar application, with a strong regional focus on the Eastern Mediterranean, sorry. Today's webinar support the mission of the project by sharing cutting-edge expertise and opening the floor for collaboration and exchange. It's now my pleasure to introduce today's speaker, Dr. Leonardo Micheli, if this correct pronunciation. Dr. Leonardo Micheli, it's an associate professor at Sapienza University of Rome. It's a leading researcher in photovoltaic system modeling with a strong focus on soiling, one of the major causes of energy loss in solar installations due to dust accumulation. His research spans from physical modeling to remote sensing and mitigation strategies, aiming to make PV systems more resilient and efficient in real-world climate-impacted environments. Today's talk with a title tackling photovoltaic soiling, monitoring, mitigation, and future directions. And at this point, I would like to give the floor to Dr. Micheli. Thank you.
Thank you, Georgia. Thank you, Rodanti, Rodrigo, Miguel, for organizing this webinar. It's really my honor to be here today. Hi, everyone. Thanks for joining. As said, I'm Leonardo Micheli. I will be giving some talks about the status of soiling as well as some recent advances, talking about the different aspects of soiling, going from monitoring up to mitigations. I think you can see my screen. The audio should be fine. Very quick overlook of where I am from Rome, from Italy, where I studied. I did my PhD in the UK, and then I had a few years experience at NREL in the US before coming back to Europe for a Marie Curie at the University of Jaén. And since 2022, I'm now back in Rome. If you ever happen to Rome, please come and visit us. We are located very conveniently close to the Colosseum. The location is beautiful. It's not as functional as many of your facilities because we are in an old convent, literally a few minutes from the Colosseum, but the location is totally worth even a touristic visit. So hopefully you will have chance to pass and say hi soon. So what we are talking about today is soiling loss, soiling, which is one of the most important losses affecting photovoltaic systems. Since we come from different backgrounds, I will be giving definition of what the problem is. I will give you some numbers related to its magnitude, at worldwide level, and then discuss also the role that major extreme weather events, in particular dust storms, can have on soiling accumulation. Then I will discuss how soiling can be mitigated and monitored, and I want to present also some ways, some current industry trends that are gonna be changing the way we handle and mitigate the soiling losses, such as saturation, clipping, electricity price, and curtailment. So when we discuss about soiling and photovoltaic soiling in particular, we refer to the accumulation of dust, dirt, any type of particles on the surface photovoltaic systems. So what happens here? We have a graphic that was kindly produced by Alex from NREL. When we don't have any soiling on top of the solar glass, some of the light is still reflected, but most of it is transmitted through the glass to the semiconducting material and can be therefore converted into electricity. However, when soiling starts building up onto the photovoltaic glass, we have an increasing fraction of sunlight that is being reflected back into the atmosphere. We have part of it that is absorbed by soiling itself, and part of it that is still transmitted but scattered, even if this is a minor issue for photovoltaics. But the overall result is that we have sunlight that reaches the photovoltaic material at lower intensity, and thus lead to lower conversion efficiency, and thus brings the panels to work at lower efficiencies. Now, when we imagine, a photovoltaic system being soiled, we typically, in most cases, people will think about desertic dust. However, soiling can have very different shapes. So we have seen clearly episodes of dust accumulation and sand accumulation of photovoltaic modules, but some of the most cases nowadays we get also reports of, for example, bird droppings, very severe bird droppings on the photovoltaic modules, as well as other type of contaminants, such as pollen, which is still very difficult to model, or other anthropogenic sources, such as agricultural emissions or industrial emissions, that can lead to some very locally high soiling accumulation rates. So all of these, again, is what we call the soiling, and all these different types of soiling accumulation are going to cause performance losses and can also accelerate degradation. Back in 2018, with some colleagues, we conducted a global estimates of soiling losses, looking at the top 22 photovoltaic markets that were available at the time. And we found out that soiling was probably already causing back then the loss of 3 to 4 billion euros. Loss that can be estimated in terms of both missed revenues from the missed performances, as well as increased operation and maintenance costs for the plant. Back in the time, we also tried to forecast what would have happened in the future, because at the time, we were expecting an increase in photovoltaic capacity, but also a decrease in electricity price. And what we found out was that even back then in 2018, we were forecasting the soiling losses to increase up to 4 to 7 billion euros because of the increased photovoltaic capacity and the increased installation of system in some soiling prone locations, such as, for example, India or parts of the MENA regions. However, we relooked at the data in the past years, and what we found was that actually our estimate was very conservative, because photovoltaic has increased at a much faster rate than that was expected. So probably the losses are already bigger than 10 million euros. And at that time, we also did not take into account that the electricity price actually did not drop, but increased. And if we do the same exercise today, we can see that the losses are expected to further increase in the future. However, soiling is not just an economic problem. It's just something that is going to affect investors because of missed revenues. It's something that, as I want to highlight in the upcoming slide, can also have some major repercussions. Nowadays, indeed, we live in an era in which photovoltaics is increasingly penetrating our grids. So this is the share of photovoltaic energy in the electricity mixes of 3 of the major European markets. And as you can see, in all these markets already in 2023, photovoltaic was providing more than 10% of the electricity that was consumed within that market, meaning that even the grids, the electricity grid, is growingly relying on photovoltaics. Well, the problem then is that, with great responsibility comes also, comes also great responsibilities. And the problem here is that if we have major performance losses on photovoltaics, then we are going to create major problems also to the photovoltaic, to the national grids. So what we wanted to look at with some colleagues from the University of Jaén was how a disruption, or a large-scale disruption on photovoltaic performance could also have national impact on the grid. And we did that in particular by looking at the effect of dust storms, and in particular to a very specific dust storm that interested mostly the Iberian Peninsula, but that then traveled also across several European countries. As I said in the preliminary discussions, I know that most of you probably knows dust storms much better than me, but just to make sure everyone has enough details, we are discussing about phenomena where a large amount of dust and sand is suspended into the airs and can travel for thousands of kilometers. These are just some typical pictures of dust storms from arid and desertic areas. And this is a significant concern, not necessarily for our community, but for example, from food chain and agriculture communities. I am highlighting here actually a press release from the FAO, so the Food and Agriculture Organization of the UN, and I'm bringing it up to highlight how dust storms are a severe concern in for different communities, but also because I found very interesting that FAO highlights as one of the major impacts of dust storms also their impact on solar panels, highlighting also how much responsibility, how much weight, and how much trust is put on our technologies. Now, as I said, these events, these phenomena can actually travel for thousands of kilometers. Those of you that live in Europe live very nearby the major source of dust dust storms, that's the Sahara Desert. But as you can see, there are several places where these events originate and several typical trajectories they can follow. Because of this, actually, there are even locations that are considered humid and rainy, where the air is considered clear, can actually be affected by dust storms. These include, for example, the UK, where several episodes of dust storms have been reported, especially over the recent years. Several reports also, for example, from East Europe and Russia. And in 2020, we had a Syrian dust storm that traveled from Africa up to the east coast of the United States and the Caribbean basin, causing also some health and safety concerns over there. So why am I talking about dust storm today? Because actually they are quite interesting for us, because they have a dual effect, or can have a dual effect on photovoltaic system. They indeed have a first concurrent effect, because as you know, they reduce the amount of radiation, solar radiation, that reaches the surface, and thus we have less resource available for the generation of photovoltaic electricity. However, since we are talking about soiling, they also lead to an increased accumulation of soiling on photovoltaic modules, meaning that the performance loss they cause can actually last even after the sky is cleared. So they can have an effect that lasts even longer than the dust storm itself. So what we really wanted to understand is, given the increasing penetration of PV in our national grid, we wanted to understand if the impact of dust storm could also have some repercussion on the national grid. And we had, in particular, we look at an extreme event or actually, a period in which a couple of dust storms took place and interested in particular the Iberian Peninsula in between March 13 to March 30, 2022. A first very intense event and a second slightly longer but less intense. So we tried as PV researchers, to quantify the magnitude of that event. And so we looked at some typical irradiance and air quality indicators, looking wherever available at both satellite, reanalysis data, as well as ground mounted. So we looked at actual weather as well as cloud-free or clear sky global horizontal irradiance data. We downloaded PM10 and PM2.5 from European Protection Agency, and data such as AeroNet from both gridded dataset as well as AeroNet. We also looked at cloud cover, dust optical depth, and other variables. At the same time, what we were mostly interested in is clearly the electric performances. So in particularly, we looked at nationally aggregated data for Spain of PV capacity, of daily PV generation and daily electricity demand. So we looked at the peninsular Spanish grid, and we tried to understand how much the PV generation varied. And we were talking about 19 gigawatt of photovoltaics at the time. We looked at how much electricity was consumed on that day and how much capacity of photovoltaic was available. We use these three variables to calculate the capacity factor, which is a metric that is telling us how well a system is performing. In particular, this is used mostly to compare different technologies, and it is defined as the ratio between the actual photovoltaic, the actual energy generation, in this case we are talking about PV generation, over a day, divided by the energy that the system would produce if it was working for 24 hours at its nominal capacity. So is the product of the PV capacity for 24 hours. Second metric we considered was the market share. So how much of the electricity demand was actually met thanks to the photovoltaic generation. We analyzed historical data in particular to decompose them and generate some forecasts using the Facebook Prophet algorithms. So first of all, we wanted to have an idea of the extent of the dust storm, and we look at the clear sky GHI. On the left side, you see the average values for, again, for the whole Iberian Peninsula, and in blue, you see the actual 2022 data, while in gray and in dotted black, you see the expected performance generated with Prophet. And as you can see, during the highlighted period, we had a very severe initial drop where we lost about a quarter of our clear sky GHI. Then we had a quick recovery, and then another drop, much less important, of clear sky GHI that then recovered by the end of the month. On the right side, you see what happened on the worst day, with most of the losses, again, in clear sky GHI, over the Iberian Peninsula, with most of the losses in central Spain, where actually a substantial capacity of photovoltaic is installed. Now, the dust storms, in addition to the dust storm, a possibly related, adverse weather conditions were present, and so these combined adverse conditions actually led to a substantial reduction in photovoltaic performance. And again, by looking at the data, what we found is highlighted in these two graphs. On the top one, we have, again, the PV capacity factor, so expected performance against actual data in blue, expected performance and uncertainty of the forecast in black and gray. And as you can see in the highlighted period, actually the capacity factor of 19 gigawatt of PV again, for a whole country, dropped from an expected 20% value to an average 10%, meaning that photovoltaics over a 2-week period provided only 50% of the energy that it was supposed to provide to the grid. And on the worst day, again, the March 16, we found a drop that was as high as 80%. So we had a 19 gigawatt capacity of photovoltaic working as if they were only 4. So significant, substantial underperformance. What this means that the grid actually, instead of receiving 10% of the energy from photovoltaics over a 2 weeks period, only received 5% of photovoltaic energy and had therefore to find alternative sources to cover that electricity demand, highlighting how we have to be really careful while photovoltaics increase its penetration to the grid to make sure that we have a flexible enough storage solution and some additional capacity to make sure that even when this severe underperformance occurs, the grid does not suffer from the missed energy. However, if we go back to the capacity factor, we can see that those, while were probably the most intense and prolonged events, were not isolated events. Indeed, there were several days over the years, we counted about 20 with the analysis we did, in which photovoltaic performs well below our confidence interval, with an average drop in capacity factors in the order of 60%. So with photovoltaic providing less than half of the energy that it was expected. And again, this was not just in 2020. If we look at the historical data, the trend is similar. And for Spain, we found that on about 10% of the days, so more or less a month per year, we have a PV system, the national PV capacity performing at 40% of its expected performance, and for 3 days a year, performance in the order of 20% of their expected values. And again, this is not just a problem of Spain. I'm currently repeating the analysis also in different countries, such as Germany or Italy, where we are also finding very similar trends. Month a year where the capacity drops by 40 to 50%, and again, those 3 days per year where the capacity is, drops by 80%. In this work that is currently ongoing, I'm also trying to understand if there are risk factors that we can use actually to identify when these underperformance are occurring. And so I've been using those data to really understand whether there is a correlation between the value of different environmental parameters and the severe underperformance. At the moment, what I have, is shown in this and in the next slide, where I'm comparing actually the value of the total cloud cover, again, at national level, on days that we can consider of normal operations and days of significant underperformance for the 3 different countries I nominated earlier. And you can already see that there is some clear deviation between the data. And, as you would expect, when the total cloud cover is higher, so when the average fraction of the sky covered by visible clouds is higher, we might have more severe underperformance. Countries such as Spain, Italy tends to have lower values on their normal days, around 0.4, but then, the total cloud cover is essentially on, the median value is double on days of underperformance. But the same happens, for example, in Germany, where, the average total cloud cover is much higher. I'm also repeating this analysis, for different parameters, as I said earlier. And, so far what I found is that also parameters such as aerosol optical depth and dust optical depth can be used as risk, factors of risk to understand whether a system is underperforming or not. On the left, you have the results for the AOD, with again Spain, Germany, Italy, as you can see, having significantly different values on days of normal performance and other performance. And interestingly, the southernmost countries, Spain and Italy, also showing a very clear difference in DOD, in dust optical depth, when for days of normal performance and underperformance, possibly suggesting that dust storms are really one of the major issues, at least for countries that are more exposed to or that are more subject to Saharian dust intrusion. As I said, this is an ongoing work, so any suggestion is really, really welcome. And some of this knowledge and much more actually can be or will be available on an upcoming report that is being produced by the IEA Task 13. In particular, I want to highlight that among the different extreme weather conditions that are assessed and discussed in this report, we also have a specific chapter on dust storms, where we discussed about potential way to monitor them and mitigate them, starting from site selection and design of the system up to improve tools for monitoring, as well as potential ways to mitigate their effects that are mainly related to limiting soiling accumulation. The report is in its publication phase, so will be available for free in 2025. So feel free, to reach out to follow PVPS, or reach out to me if you want to have more information on that. Now let's go back to soiling, which again is the main issue that we want to discuss today. And it's a particularly interesting loss in photovoltaics because soiling can be mitigated. So we can put in either preventive strategies to limit the accumulation of soiling on the modules, or some corrective strategies to actually remove the accumulation, the soiling that has accumulated on the photovoltaic system. Unfortunately, we don't have much time today to go through all of these, but the message that I want to send out today is that still nowadays, there is no real way to avoid the need for cleaning the photovoltaic modules. That's even, if nice preventive strategies are put in place, it's very likely that a cleaning will be needed. So a mechanical removal of soiling will be required. We have different ways still nowadays in which modules are cleaned, depending on both the soiling condition, the system design, as well as the local economic conditions. Indeed, we can go from fully manually cleaned photovoltaic modules in those locations where the labor cost is lower, and where not much not much funding are available for investing in high tech, very costly robots. For example, this is a technique we, for example, see very often in India. On the other side of the spectrum, we have fully automatic system, where we have robots mounted directly at the end of each photovoltaic array, and that operate autonomously every night, every 2 nights, once a week, but that anyway do not require any human intervention. Again, these require very high initial investment, but then a very low running cost. The intermediate solution we found mostly in Europe, in the US, where soiling is intermediate, actually is what we call semi-automatic. So cleaning itself is performed through a device, but we still need a human operator, either to operate a truck where the cleaning device is set, or, for example, to move the robots, as in this figure, or to move the robots from one row to the other. Anyway, in any case, any solution we decide to go for, we have to consider that we will have costs involved with cleaning the photovoltaic system, either because we need an operator, either because there will be expenses related to resources such as water or parts that will have to be converted. And so it's very important to schedule the cleaning strategy in a way to maximize the difference between the revenues that one can make from cleaning and the cost of cleaning itself. So, and the most easy way to understand how to calculate revenues is to imagine it as a product between the recovered energy, so the extra energy we gain after cleaning the system, multiplied by the electricity price. And this has been, the very in first approximation, the equation that has been used to the community to really understand the value of cleaning. So what we need to understand in order to evaluate whether cleaning is profitable or not, the level of the losses and the electricity price. And there are different ways nowadays we can monitor the soiling losses, so we can understand how much soiling is affecting the energy performance of the system. And the most common way is a soiling station, such as the one that you see here in this slide, where we have two different modules or two different cells exposed under the same conditions. One of the two PV device, in this case a module, is regularly cleaned. And so we can estimate the soiling losses simply by comparing the output of the two photovoltaic devices. Now, as I said, in this case, we are using two modules, and these were cleaned by a human operator every 2 weeks. But in some cases, right now, you can also find soiling stations that automatically clean the reference device through either high pressure jets or some rotating brush. Now, since a few years, however, we have also seen some innovative designs and solutions being proposed. These are known as optical sensors, and instead of taking an electrical measurement, such as on this left soiling station, they are actually trying to estimate some optical characteristic of soiling, either their reflectance, such as in the case of the dust IQ Kip and Zonen, or again, the brightness of the pixel in the field of view of a camera exposed to soiling, such as in the case of Mars, and then convert this optical measurement into this optical measurement into an electrical loss. The need for such sensor came from the need for low maintenance solutions. Solutions like these two on the right do not need water to operate, requires very low maintenance, and tend to cost less compared to traditional gold standard soiling stations. However, over the years, we have also seen different ways to estimate losses that would not require some specific hardware. And this approach that we have been within the community referring to as estimation models are particularly useful when you have to understand or select a potential site for a new photovoltaic installation, and you don't want to run an experimental campaign with a soiling sensor and delaying your soiling assessment and then installation phase by 6 or 12 or 18 months. So soiling is being and has been actually estimated from environmental parameters. Indeed, we have a number of soiling estimation models that, if provided with environmental parameters, I will show which one, as well as some key information about system configuration, are able to provide to us a soiling loss profile. So how do these estimation model works? They're mostly based on the assumption that a soiling profile can be approximated to a sawtooth wave. So in this chart, what you see in black are some actual soiling measurements represented in black and reported or expressed through the soiling ratio. You can imagine the soiling ratio as 1 minus the soiling loss. So we have a soiling ratio of 1 in clean conditions. And then as soiling starts building up, on my photovoltaic modules, I start having my soiling ratio decreasing, okay, as you clearly see in this curve. So the more soiling accumulates, the more the soiling ratio decreases until when a cleaning occurs, okay? And when the cleaning occurs, we have steep and rapid recovered in soiling ratio or a reduction in losses, and then soiling starts accumulating again. So what do these models do? They use essentially two different algorithms, one to identify the slope of this trend and one to identify when natural cleaning events occurs. Well, cleanings are typically attributed to rainfall, and typically a binary approach is used. If the rain intensity is bigger than a given threshold, then a full cleaning is assumed. Then the accumulation rate is typically linked to the particulate matter, either PM10 or PM10 and PM2.5 together, in order again to estimate how much of the suspended dust is likely to deposit onto the module. Different models have been proposed in literature, but they have not been yet widely calibrated and validated. Just to give you an example, here there are actually three different models, used with different combinations of data and assumptions, compared to some actual soiling data represented here by the black dots. And as you can see on the left image, for example, we have a couple of models, the one in purple, the Bergin model, and the one in green, which is a mixture of two models, a Coelho model and the U model, that perform quite well and actually overlap in most cases the actual soiling trends. However, if we apply that same model, taking into account the different system characteristics to a different location, what we found is that all the models, including the one that were performing well before, are overestimating the losses and thus underestimating the soiling ratio. So I just want to highlight that a lot of research is still needed there, because we don't have yet a universal model that we can apply to estimate the soiling losses, even if these have been used both for research purposes, as you see, for example, in this image, where we recently produced soiling maps of Europe, assuming, for example, a perfect cleaning by rain, and however, also but there is still some research to go on, because even the assumption of a perfect cleaning can be disputed and has been disputed, for example, in our work, where we presented, according to some empirical evidence, how this map would change if, for example, non-perfect cleaning was assumed, because, induced by the rainfalls. So again, there are different challenges there that will have to be addressed in the upcoming years. However, I also want to give some future perspective. And so, to do that, I invite you to consider that a perfect model existed. We were able to estimate how much losses were occurring because of photovoltaics directly from the environmental data. Well, in that case, we have to take into account that actually the way we are installing and operating photovoltaic system exists. And thus, the losses that we might monitor, that we might expect, are not those that are going to be visible. What I mean is that the losses that are occurring on the DC side, so on the modules, are not necessarily the one that we see on the AC side of the system, that the grid is gonna see, because we have new mechanisms taking place that are actually gonna lower the amount of energy that we can recover thanks to the cleaning, and thus are gonna affect also the revenues that we will have available to estimate whether a cleaning is convenient or not. Some of these mechanisms include inverter saturation and curtailments. If you're not familiar with those, no worries, I will try to give you a very quick overview of those. So inverter saturation is actually a phenomena induced by the industry trend that has been going on for some time. Here on the right side, actually what you see, let's focus on the green bar that shows the average value for PV systems installed in the US, is actually the ratio between the capacity of the photovoltaic modules and the capacity of the inverter. Okay, you need the inverter to convert the DC current produced by the modules into the AC current. So what is happening here? We have a capacity on the DC side that was 20% bigger than on the AC side, than the inverter size, but that has now actually grown to 30 to 40%. So what does it mean? That if the photovoltaic modules are working closer to their nominal capacity, the inverter will saturate and will not be able to convert all the energy produced by the modules into energy that can be injected into the grid. So let's have a look at this image on the left, where you see a typical PV performance profile on a clear day. And here we have our AC to DC ratio. Clearly, this is lower than 1 because the inverter, the AC side, is smaller than the DC side. Let's imagine we have a 1 kilowatt system. On a clear sky day, it might produce on the central hours of the day up to 80, 0.8, 0.85 kilowatts, okay, at peak power. Now what is happening? Our inverter is 30% smaller than the DC side, so actually can convert only approximately 0.7, 0.75 kilowatts. What is happening then? All this region highlighted in red is going to be lost. All that energy that could be produced by the modules is not going to be produced. Okay. And so what we see from the AC side is only this part of energy. Okay. Up to this level, we are losing all this part. Why does this matter? Because actually any soiling loss that might occur here is not going to be visible from our side during the central hours of the day. And so if I clean my system, I will not see any energy that I recovered during the central hours of the day. So we did with some colleagues from Sandia and NREL some analysis to really understand the extent of this phenomena and the impact of clipping onto the soiling losses. So we developed a model starting from 5 minutes NSRDB data and using a traditional soiling model, developing our very simple in-house clipping model, which was then validated using data from PV Fleet. Here in black, you see how our model performs compared to the actual data shown in red. And the models is also able to tell us how the system would have performed if clipping was not present. Here, you quickly see how we calibrated our soiling model using actual data provided by Sandia. And then we run a US-wide analysis, try really to understand how much clipping and inverter saturation is affecting the soiling losses. So what we found was that for an inverter loading ratio of 1.34, so an inverter about 30% smaller than the DC side, actually in a country that experienced soiling losses up to 8 to 9% on the southwest of the southwestern region, we actually have an absolute reduction in soiling due to inverter undersizing that is not bigger than 1%. So what does it mean? That yes, we can get reduction in soiling losses up to 40%, but that occurs in those regions where the soiling losses are already small. However, in those regions where soiling is intense, under these conditions, the masking effect of soiling is not as dominant. However, we have to take into account that if we imagine increasing the inverter loading ratio, for example, to 40, 50%, and we imagine system performing better, actually we might have an absolute reduction in soiling losses of 3%. And if we are able to reduce, by 3% absolute, 80% soiling loss, it means that we might be able to reduce the problem of soiling by 30 to 40% relative. So even if it is not now a solution, Stalling might be masked in the future by inverter loading ratio. But at the same time, we have to be careful because as degradation occurs, systems over the years will be performed at lower and lower efficiency. And so the inverter saturation conditions will be reached less and less often. And so even if soiling is initially mitigated, it might become more and more a problem as the system ages. So as you can see, as the photovoltaic industry evolves, the soiling problem is becoming more and more complicated. A different issue is actually related to curtailment. Very quickly, curtailment is a restriction that the grid imposes to the maximum amount of energy, of solar energy that can be accepted. So what is happening now? We are producing so much solar energy and so much concentrated in the central part of the day that in some cases, actually, the grid might say we are not going to be able to accept part of the solar energy that you might want to sell us. So what is happening? Part of the energy is going to be curtailed. Again, we might not be able to sell part of the energy that we produce. And again, why is that affecting soiling? Because we might think we need to clean our system, but in reality, any extra energy that we recover might not be sold to the grid. And this is an increasing problem in different countries. We recently studied, for example, the case of Spain. And here on the left, you see how much photovoltaic energy is being currently curtailed. And as you can see, since March 2022, or April 2022, when curtail was first imposed in Spain, actually numbers have increased and reached values close to 4 to 6%. So again, this is something else we have to take into account because can have repercussion on the way we measure soiling and we mitigate soiling. However, I just want very quickly to close this talk by stating that to calculate the revenues, we also have to take into account a second parameter. First of all is the recovered energy. And as I said, the way we operate system is changing. And so actually the recoverable energy might be lower than we expect. However, we also have to take into account how the electricity price is evolving. And as you know, at least in Europe, most of the electricity is sold in spot markets where the price changes continuously. We don't have much time to go into deep into how the market works, but this is just, to give an idea of how the electricity price has been changing since 2015 to the end of 2022 in three, major European countries. So until 2021, it was normal to have electricity price below 100 euros per megawatt hour. But since then, prices have been changing dramatically, reaching also extremely high daily values. High prices actually will incentivize more cleanings, while lower price clearly reduce the incentives to clean because I see less revenues from each cleanings. And while, this chart might give you, might suggest to you that, the effort for improving the performance of the system will increase, we actually have to take into account that the price of electricity is significantly changing even in its daily behavior. On the left side, you see again, for the case of Spain, how the typical daily value, so the hourly value of electricity price has been changing compared to the yearly average. So a value, for example, here at 5 o'clock, for the blue line, lower than 1 means that at that time, typically the electricity was sold at a price that was lower than the yearly average. A value bigger than 1 suggests that at that time, typically the electricity is sold at a value larger than the average values. And what do you see? Photovoltaics typically perform the most in the central hours of the day. And since 2020, we have been experiencing a very severe drop in the central hours of the day when low-cost renewable energy are sold and thus bringing down actually the cost of electricity. What this means is that we should not only look at the average values, but we should actually look at how the hourly values is changing, because photovoltaics is being particularly affected by that, actually because of itself, because photovoltaic energy is offered at a low price, and it does bringing down an electricity price. So we have to take into account that actually selling the energy in the central part of the day might give us lower reward compared to what we would have otherwise. And that's where batteries actually might be able to counterbalance some of this perspective, because we might be able to store part of the recovered energy that we got from cleaning and selling it into a higher price period. So overall, what I wanted to give you today was an overview of soiling. We started by discussing extreme weather and the likely impact that even factors such as AOD and DOD can have in predicting PV underperformance, even at large scale. Even if multiple soiling mitigation strategies exist, we have to take into account that cleanings are still necessary. But we also always have to balance revenues achieved through cleanings with the cost of cleaning itself. And we have to take into account the new industry trends, such as inverter under sizing and saturation, as well as grid curtailments can actually affect the amount of energy, the revenues we are going to be able to make thanks to cleaning. And similarly, also the lowering electricity price might actually reduce our incentives to clean. I wanted to close with a good note showing how, on the other hand, battery energy storage systems might be able to counterbalance some of this perspective, because we might be able to store some otherwise clipped, otherwise curtailed energy and sell it in period of high demand and higher price, resulting therefore in increased economic returns for soil mitigation activities. So thanks to all of you for attending the presentation. Hope was clear and interesting.
Thank you very much, Dr. Micheli. It was really interesting, this presentation, and also very important also for our region, for Cyprus, because we are suffering from all this dust event, and the soiling, it's a big issue. There are some questions in the chat. Until now, there are 4, so I will give the floor to the following the order of the questions instead of just reading. So I would kindly ask Kritika to send your question.
Thank you so much. I have 2 questions actually, and it might be basic, but it's just for my own clarity. First of all, thank you so much for the presentation. It was really nice, and I have been following your papers as well on soiling. So my question, first question is, are these soiling estimation models able to estimate the hard soiling as well? And if yes, how? And if not, what methodologies can we use to determine these without the use of, dust IQ and those kind of sensors?
So thank you for your question. I think with hard soiling, you refer like to pollen or micro or biofueling, or what do you mean with the hard soiling?
Like sometimes because of the rain, it doesn't get fully washed, so it becomes more sticky, and then it just keeps getting layered. So in that case, if you're going to see the PR or the drop in the trend, you see the drop with whatever was eliminated because of rain, but the hard soiling or the some layers still there, which is I feel not being able to detect by the slope in what we're trying to calculate with respect to the PR.
So thank you for this question. It's really timely, and actually, yeah, that is one of the big problems. Is really related to the way we model cleanings, because nowadays perfect cleanings have been mostly used. Someone has used some gradual cleanings, but there is evidence that rainfall is not enough to fully clean a PV module. So there are actual ongoing works on that. I know colleagues from DLR in Germany, but actually in Almeria, are really studying this because the main assumption has been a perfect cleaning, and that has been misleading, especially in those regions that are not extremely arid, or where soiling is, or when the system is not tilted enough. So unfortunately, I think that's one of the main limitations. Sorry.
Okay, and the second question was with respect to the clipping itself. So I think one of the inputs, for example, in the time series decomposition using Facebook Profit, the input is like the PR or the NPR. So when you're calculating those values, how do we take into consideration the clipping part? Because in that case, there shouldn't be an unnecessary drop in the PR due to clipping, which then should not falsify that there is a soiling and it can be due to something else.
Yeah, so I haven't been using. When I use Facebook Profit, likely that event took place before curtailment. So yeah, there was no drop related to that. But yeah, clearly when you use Facebook Profit with PV performance data, you have to be sure that there is no especially because these are very seasonal, tends to be seasonal. So yeah, you have to be sure to understand when clipping or when mainly curtailments are occurring. Yes.
Okay,
But luckily for our analysis was before curtailment took place.
and the final question is when you're actually trying to optimize the cleaning schedules,
Yeah.
do you also consider the future rain forecast as well to see, because if you're trying to do the revenue generated to see when we are going to do the profit, so maybe at like let's say from 10 days from now, it is actually reflecting that that is the point where it has to be cleaned. But if it's going to show that there is rain in another 3-4 days, does it take that into consideration while doing it?
So yeah, so what has been done typically is you cannot really work deterministically, so you have to work probabilistically, and look at historical rainfall pattern and understand what is the chance of raining occurring in a given period, and so predetermine your cleaning schedule. Also because most cases you have to schedule a cleaning 1 week, 10 days before, because again, in Europe, US, you have to call for a third party to come with a truck and so I don't, real-time forecasts. I understand, you can rely on them up to 3 days in advance, and that might not be enough to call off cleaning. So again, you have to look probabilistically and say, probably based on the past 30 years, it's better for me to clean on these dates. And then, I mean, if cleaning is that reason, if their season has been particularly clean, you might then rethink about that.
Thank you so much.
Thank you. Thank you.
Okay, so we can continue with the questions on chat, and after that we will go to the people who raised their hand. So I will ask Jim Joseph to set his question.
Hi, Leo. How are you? Nice to see you.
I'm good. Hey, Jim.
My question was around the sawtooth soiling ratio that you showed. I know typically it has been done considering rainfall as the cleaning event. I wonder how it would look like for non-rainfall type of cleaning events, such as this robotics or the manual cleaning or the tractor-based cleaning. Will it look the same or will it be different? And also, given the fact that especially if you look at tractor-based cleaning, because these panels are not cleaned at the same time or the same day, they actually is done over the days. So if you want to clean the whole solar panel, whole solar farm, it'll probably take a couple of days or maybe few weeks based on the size of the solar farm. So then, assuming a rapid rise to soiling ratio equal to 1 is probably not the best there. So yeah, I'm keen to hear how you tackle that, or has that been thought of before?
So thank you, Jim, for your question. I believe commercial products that you see around, they take into account cleaning effectiveness, depending on the type of cleaning you apply, maybe slightly lower for completely dry cleaning, slightly better if water is somehow involved. And then they take into account a typical velocity for the for the cleaning process. So that will consider that not the whole system is cleaned at the same time. It might take a couple of days. So that is considered most in commercial software. They are starting considering that. And regarding estimation model, clearly you have to input yourself when the system when the system is gonna be cleaned or was cleaned. So that is the type of input you have to include. And regarding additional cleaning, there is ongoing discussion about wind because it might have a double effect. Some cases it worsens soiling. So I know very limited number of studies that have tackled that, and there's not been considered much. Other environmental parameters that have been considered, like rainfall, to really understand how the accumulation rate has been varying. But we clearly need to consider all of those, as well as the effect of dew, for example.
All right. Thank you very much, Leo.
No,
thank you for the nice presentation.
Thank you.
Okay, thank you. And we will proceed with Kilian Lobato.
Hello, good morning. Thank you for the question. First of all, apologies if this was already addressed earlier. I unfortunately missed the start of the talk. My question is, when the actual production falls significantly below the forecast for several days, what are the main reasons why the forecasting models fail to anticipate these dips? Are there particular factors or data limitations that make these events difficult to predict?
Sorry, you were discussing, referring about the prediction of extreme dust. So that was purely based on a univariate forecast. So did not take into account, any additional, any environmental conditions. Okay. So it was purely based on the typical trend of the curve.
Okay. All right. Thanks.
So we wanted to understand which, variables actually could be moving away the performance from their expected values.
All right. Thank you for that.
No, thank you.
Okay, so Miguel.
Thank you. So two quick questions. The first one is about the value of anticipating soiling extreme events. Is it reasonable to, if I own a single axis PV power plant, to put my panels on the vertical to avoid soiling when the dust comes?
I mean, it would be nice, but clearly you have also to consider the wind conditions. There are studies showing that increasing the tilt angle or even inverted stowing would reduce soiling accumulation. So that is one of the mitigation strategies that could be considered if the wind conditions allow for it.
But they're often not used.
No, there is. At least I don't know. I'm not aware that if they are used or not.
Okay. The second question is a practical one. Is there a network of soiling measurement data?
There is not that I'm aware. If you mention, different location using, measuring soiling similarly and sharing like BSRM, no, there is not. There are individual person measuring it, but it's very hard to find publicly available soiling data.
Okay, and then very final comment. There's on slide 42, when you were talking about the electricity price.
Yeah.
I would suggest that you think about, not necessarily correct, maybe talk about the median value of the price of electricity instead of the average. I think
Okay.
that would be maybe better.
Okay, thank you.
Thank you.
Okay, Kilian Lobato, do you want to add something on this?
Sure, maybe just a cheeky question. Leonardo said that there wasn't any good public data on soiling. I'm wondering if he knows if there's good private data on soiling.
Ground measure, not that I'm aware. I don't know if Jim John knows anything. I know right now most of the maps that are available are mainly based on combining reanalysis data with estimation models. So not that I'm aware.
Okay, thanks.
Okay, I see some more raising hands. So Hossein Panahipa.
Okay, thank you, Leonardo. Can you hear me?
Yeah.
Thank you for your nice presentation. I'm Hossein from Dakar or Limassol. I have a couple of questions. Let me first ask the second one because it's discussed by the previous person. Related to the soiling data sets. Here in the Limassol, our group is mostly concentrated on the monitoring of the atmosphere. We use the ground-based and satellite recording. So how we can integrate this data set related to the AOD or DOD and bring it to your application? Is there any specific way that you can explain it right now? This is my second question. And the first question is related that yesterday we had a very interesting and useful training by Rodrigo related to this PV modeling and the predictive of the output of the PV model. And it was a discussion related to the environmental parameters, such as the temperature, humidity, and something like this. How do you think it is possible to bring the soiling impact into these models, or it is useful, or there is not any way to do that?
Okay, so thank you for both questions. So regarding your last question, yeah, it is typical. So it depends. In some cases, soiling losses are included in the fixed performance losses that you apply to when you estimate the energy yield of photovoltaic modules. I think PVGIS, I don't know if you discussed about that, but typical models assume a fixed 14% loss, and that includes a 2% soiling loss. The most common energy yield tool for PV is PVSYST, and I think they recommend a 2% per month soiling loss, independent of the location. Ideally, what we would need is really to reduce the available DC energy according to the soiling ratio. So the soiling ratio is calculated like that, so you can directly multiply it by the energy yield. And again, it depends whether you can measure it or calculate it through environmental conditions using some model with which you are confident. So that is something that is done. What is important is not to apply it directly to the AC current because of the reasons I mentioned. So your first question, the other question, let me know if I understood it, was about how can we use AOD and DOD. So, tools like, I don't remember the exact name, but, the dust storm tracking platform that was launched by Copernicus probably 1 year ago, are extremely valuable because they can really inform on whether these type of intrusions can happen on photovoltaics. And if mitigation strategies are available, that would be valuable. DoD, I think, is interesting because our community has not been looking much at it, at least the wide community. Sorry, and again, I think it can inform, can be used to inform about soiling losses and potential reduction in power generation, maybe even better than PM10 and PM2.5. So, if you have those data, if you have some PV nearby, PV performance data, I think you can do some very interesting work related to that, understanding again how PV performance might change depending on DoD, and if any soiling accumulation, more severe accumulation occurs.
And we're very close to the end, so I will give the floor to Rodrigo.
Thank you, Rodanti. Thank you, Leonardo, for accepting our invitation. It was really good to get to hear your all the experience you've accumulated throughout the years in this very summarized presentation. My question relates to PV cleaning in industry. So it's easy to guess that in very soiling intensive regions, companies clean the panels using different strategies. But from your understanding, like except extreme events like we had in the Peninsula of Iberia, do countries like Spain, Portugal, Italy, is cleaning a regular thing in the large scale industry?
So it's something, thank you for your question and thanks for the invitation. So yeah, it's something that is being considered, or let's say that the southern regions tends to consider more compared to the northern, some northern regions. Clearly, in Andalusia, they are aware that cleaning is important, and so that is significantly taken into account. I know that northern part of Italy, for example, might not be so, and that can be a problem because even if you don't clean your system for 1 year or two, then it might be it might accumulate. It might become very hard to remove it. Also, we are not fully, so we start understanding the impact of pollen, for example, on as a soiling element on PV panel, but that is extremely difficult to track and model because my understanding is not as systematically organized as aerosols. So yeah, it depends on the location where you are, and it's important to take it into account because also the design of the system changes depending on your soiling decision. If you need a truck to go through your system, you have to distance your modules enough to let that happen, and make sure that the site is accessible. So I would say that some regions, those are more affected by mineral dust intrusions, companies are aware. Mainly talking about Europe, in the north is not as commonly taken into account, and some very easy assumptions are made, like again a fixed 2% losses in Denmark, which might be unrealistic.
Thank you.
Thank you.
So I cannot see anything more. We are close to, it's already 1:30. So I would like to thank again Dr. Micheli for his presentation, and of course all of you for participating to this webinar series. This was our first webinar, and looking forward to invite you and to see you to the next one. Thank you very much.
Thank you, everyone, and thanks for organizing and inviting. Ciao.
Bye. Bye-bye.
Bye.
Thank you.